All right. So hello and welcome to this webinar on understanding negative phase sequence overcurrent and broken conductor protection. Thanks so much for joining us. We've seen a fantastic turnout for this event today, and I hope that the information that we share with you today is going to really help improve your practice and your understanding around these concepts. And during the course of the presentation, if you have questions or if you have anything that you'd like to feed back, you can use the console on the system. There is a question section. Those will come through to me on this side, and we will have time at the end of the presentation to go through it and answer as many questions as possible. Anything that we don't get through today, because there's quite a lot of us around, we'll make sure that we cover those off in an email afterwards. But hopefully that we achieve our goals of being able to share some information, and that really we can learn a lot from today's event. Now, before we get started, the first thing that I want to just cover off is, since we're talking about protection engineering, it is a serious topic as well, and we should just provide a quick legal disclaimer to say that the information that we're providing here is of general informative nature, and it doesn't take into account your own unique network requirements. So please consider this as your first starting point for your own research in this area, and that it's a really good baseline and an overview of what it is. But for any applications that you use this for on your own network, you'll need to do your own feeder studies and your own research to validate before taking that on. Okay, so disclaimer out of the way, let's get stuck into the presentation. So today what we're going to cover is a basic overview of symmetrical components and where that comes from, a little bit about power system faults revision. And the main reason we need to do that is to make sure that we're all on the same page for the negative phase sequence protection and the broken conductor protection stuff that we're going to cover a little bit later on. Now, we've got a really diverse cross-section of people in this session, so hopefully there's something there for all of you. And really what we're trying to do here is take an engineering approach where we can understand the basic principles behind the operation of these more esoteric functions. Then at the end, I'm going to give you a couple of practical examples about what sort of currents and voltages you would see in the event of a broken conductor, and that how you can use, say, the protection included within an OSM recloser system to be able to address those. So if you'd like to stick around to the end, then we can have an opportunity to work through those. Then we'll provide a summary and have a little bit of time for question and answer. All right, so let's kick it off. First things first with the first principles, and that is that we're going to cover phases. Phases are an electrical engineer's best friend, certainly one of my good friends, and phases are an engineering simplification for calculations. Now, the reason why it's so useful for us is that we can assume on the network that under system normal that all the frequencies are going to be the same, and therefore when you're looking at the signals of your currents and your voltages across different points on the network, you can relate them all because they have the same frequency. So the only attributes that we actually need is the magnitude and the phase. And on the right hand side there, you can see one of my favorite drawings for how this can be represented to show a sine wave, simply with the phasor, and it's rotating, and you'll see that the phasor is really a time snapshot of that individual component. Not particularly interesting when you're looking at just one of them, but when you're looking at multiple ones, it starts to be a little bit more evident why this is so useful. Because if you have a reference point, then you can tell magnitude and phase based on that reference point across an entire complicated network. So these phases actually make our calculations a lot more simple than what it would be if we had to rely on all the time domain stuff too. So they're used for many different measurements. They're used for voltage and they're used for current. And I can assure you that today in your practice as electrical engineers and as electrical technicians, you are using them every day as well. Maybe not explicitly, but through the equipment that you use to achieve those outcomes. So that's your individual phase and phasors. And in the network, we have a three-phase power system. So you can see in this arrangement here, we've got just a very simple ungrounded system, Y connected on the left-hand side, three-phase generator, three-phase load, where the relationship between each of those phases is 120 degrees. So sometimes called phase A, B, and C, or red, white, and blue, or in today's case, red, magenta, and blue. But there is a 120-degree delay from phase B through phase A, and for phase C to phase B. This is everything in a normal scenario. So you have your voltages, you have your currents, and you have phases associated with each of those measurements. So again, if you have any questions for these, feel free to use the questions console on the side here. They will come through to us. We'll address them during the course of it, but feel free to send those through. So in summary, we're using the phases to represent the measurements that we get on the network, and it's enabled by assuming that we're following a standard frequency. Now, phases capture the magnitude and the phase relationship to a reference. So if these things are so great for being able to understand what's going on in the network, why do we need anything further than that? And the main case is that things are not always so perfect. The problem is that phases alone are certainly not enough, because the majority of faults that we have in the network are asymmetric or unbalanced. So just because you know something about one side of the phase or one phase alone, you don't necessarily know what's going on the other sides, or in the voltages, or in the currents, or the relationship between those. Now, if 80% of the faults don't have that relationship, it becomes really difficult to analyze what's going on in the network. So we introduced this concept of symmetrical components to transform all of that phasor data into something a little bit more meaningful. Because if we have all of that information, then we can look at how many of each of these sequence components we have, and you can infer what kind of fault or what is the system's condition based on that analysis. Now, this, as a bit of history, came from Charles Fortescue's paper in the early 1900s. So most of the electrical network has been built on this principle. So it is as old as the hills, but it is also something that's greatly misunderstood. And one of the reasons why negative phase sequence protection and broken conductor is not an incredibly common protection function worldwide. But hopefully by the end of this presentation, it will be worth some experimentation to see if you can address some things we don't cover today. So let's introduce those symmetrical components, right? They're a mathematical transformation of the phasor data that we gather from each of the individual phases, whether they are currents, voltages, or impedances and power and so on too. It takes that unbalanced phasor data and it gives you a result of three balanced components that we know something about. So if we know what the what I1 is, we know what each of the individual legs are because there is a relationship between each of those. And in the positive sequence case, it's a 120-degree phase shift in the conventional rotating direction. For the negative sequence, it's basically the same, except you're rotating in the opposite direction. And lastly, the zero sequence makes up for any leakage in the system. I think one of the best ways to be able to understand this is to use the analog of three different coordinates in a coordinate system. So say if you have a vector in three-dimensional space pointing in any direction, it will have some x component, some y component, and some z component. So when you add them all together, they make that individual phase. Now, this is kind of the same thing, except we're applying it to the signals that we see for the currents and voltages. So the reason we do this is that we inherently get the balance back, and we can extract new information about the relationship between all the different phases, and we can detect specific fault types. Because if we looked only at the phase magnitude that we saw in an individual phase, it's going to miss a lot of the information that we only understand in the broader context of the electrical network. So let me show you what that looks like. Here we've got an example of an unbalanced phasor set. So that is the voltage on phase A, voltage on phase B, and voltage on phase C. And as you can see, it's in an awful state. Now, if we wanted to analyze this on face value, if you looked only at VB, for example, you might not necessarily know just how bad it is on the other conditions. But if we do a phasor transform, where we take this information and we convert it into the sequence components, we get something that looks a little bit like that, where we have the positive sequence part, say the X domain, let's call it that, and the negative sequence component, a little bit of Y, and then the zero sequence component, a little bit of Z, to give you the sum of all of those together. Positive sequence being if things were all normal and you have a lovely 120-degree shift, everything's nice and balanced. Negative sequence is the same, except rotating in the opposite direction. And lastly, the zero sequence makes up for the fudge factor of the leakage current out of the system. And just to prove that that is the same thing, if you sum them all together vectorially, you get this. So you can see, let's just look at the red one. If you look at the positive sequence component, we get the first line up, and then the next small component is the negative sequence, and then lastly, that VA0, that we're using the equivalent of the phase there to explain it. And it shows how that you can derive each of these sequence components out of an unbalanced condition. The other great thing about this is that if you have that information, you only really need to care about, in this case, the red line, because we can infer the green and blue lines out of the red line data alone by itself. So what I'm going to do is just quickly share these with you, and they do look a little bit intense at first, but really what we're doing here is this is the transformation where we go from the phase world, or the things that we just read directly off of the device from the CTs directly from the system, and then we convert them into the sequence domain. And that's where we get our individual sequence components. Now, usually when we deliver this as general training topics, we do this, where we have a basic example and a phasor transform where I give you 3 different individual phases here on the screen, and task the class with going through and converting these to symmetrical components, positive, negative, and zero sequence. So by way of chat, would anyone like to have a quick go at that? I think maybe today what we'll do is we'll go through these individually and we'll see whether you can follow along as we go. So let's first work on the positive sequence. Now we have the positive sequence formula down below here, the V1, which is equal to a third of VA plus A VB plus 2A VC. We have a look, we just sub in the values, and then it gives you the positive sequence component for it. It is a rather simple transformation to be able to do that. And it's the same thing that we can apply to work out then what the negative sequence component is from the phasor measurements, which you can see again, all we've done is sub in those exact same values, but because we have the different angular operator, it gives us a completely different result where the magnitude is actually much smaller and the angular shift is very different from the previous one as well. So lastly, we can have a look at the zero sequence component here, where it doesn't have the angular shift. We're basically summing them together, and it's very similar to working out what the residual is. And there is actually a relationship between the zero sequence and the residual current, where the residual is really just 3 times the zero sequence current, if you were to look, or zero sequence voltage. If you were to look just individually at the phases, sum them together, you get your residual, and then you divide it by 3 to get the zero sequence component of that too. So there's your 3 different components based on what we have there before. And just to prove that this is actually how it works and fits together, I've got the example there, VA, VB, and VC. So firstly, let's add the positive sequence to that component. We've drawn the vector here. We add the negative sequence to that component by connecting each of those tails. And then in satisfying mathematics, where we have the connection for the last component there too. So it proves that you can take a really unbalanced scenario, something that's very difficult to understand and do calculations on, and then convert it into the sequence components, which we can use to derive different understandings about what the network is and create a representation that works better in a more simple way for us to understand. All right, so with that in mind, so we've taken the volts and the currents to be able to work this out. Now, just as you can apply this principle to voltage and current, you can actually apply it to impedance as well. And this is something that we use for doing fault calculations, right? Because just as you have the positive, negative, and zero sequence currents and voltages, then obviously V equals IZ in the AC domain, our favorite equation as electrical engineers, we can rely on this to actually calculate the fault magnitudes. And what I've got below there is the Thevenin equivalent circuit for the positive, negative, and zero sequence components in place. Now, Deriving the impedance for each of those is beyond the scope of this presentation, but you'll see for broken conductor, we can actually get around that, and we don't necessarily need to derive that in great detail. A couple of general practical notes here to understand is that the positive sequence impedance is generally going to be the conventional line impedance and the sum of what happens in the system normal condition. Negative sequence impedance is generally fairly close to what your positive sequence impedance is. The only exception is when you have a lot of motors or rotating machines or generators on that network that can feed it. The reason being is that let's assume that you're running a 50 hertz network. The positive sequence is always rotating with the rest of the network, but the negative sequence is rotating in the opposite direction. Now, if you apply that to a machine that's impedance has an inductive component, relative to the spinning direction of the machine, you're actually going in the opposite direction at the same time. So negative sequence can appear as 100 hertz, which is twice the frequency of what the scenario is. What that basically means is that your negative sequence impedance, because it's an inductance, the higher the frequency, the higher the impedance, you're going to get a slight increase on a negative phase sequence impedance there as well. The zero sequence impedance has a lot to do with your earthing scheme that you have in place. And if you have a fault, it also has a bit to do with what the fault impedance to earth is as well. So I want you to keep that in mind. If you have any questions about what we've got to so far, please submit them through the question channel. I've got a few of them here already. But if you can just drop them through, at the end, I'll group them together and we'll go through them individually and make sure that we can cover those off as well. So please keep that in mind. All right. So in summary, symmetrical components are a conversion, right? We're taking the phasor values that we read, we're taking the voltages, the currents, and we're using them, and we're deriving symmetrical components from it because it allows us to derive new information from the phasor readings of current and voltage. It simplifies your calculation, really. Yeah, it's not as easy as simply looking to see what the magnitude of current is on an individual phase, but when it comes to working out what's going on the network, it does make it a lot easier for us to work from. So when we do this, we get sequence components and we get a bunch of information about whether there's overcurrent, negative phase sequence, earth fault present, right? Which brings us to the next part of the presentation where we actually start to look at these individual different fault cases on the network. So fault fundamentals, for those of you who've just joined us, is any abnormal flow of energy in an electric circuit. And really, when it comes to distribution networks or in transmission networks, you can broadly categorize most of these faults under these individual fault types. And the key is, as protection engineers, is to trip when one of these things happens and not trip when they don't. So you want to have selectivity and specificity of these faults and be able to look for the symptoms in the data that we retrieve from the network to be able to provide a response to them individually. Now, since we've already had a look at the conversions into symmetrical components for voltage and for current and the Thevenin equivalent series, each of these different fault scenarios creates a new network topology, because under system normal, you're only ever hooked up to the positive sequence network. But as soon as you introduce these abnormalities, whether it's line to line or a broken conductor or a single line to ground, you're going to have a different connection topology that's going to give you different amounts of negative sequence and zero sequence and positive sequence. So you can then design your protection schemes based on detecting each of those individual cases. And what's interesting is, particularly in the broken conductor case, overcurrent and earth fault probably won't spot it. And that's why it's so important to understand what the outcome is going to be and what the symptoms look like so that you can understand it and develop a protection scheme to be able to address this protection functionality. So I'm going to start with a really simple one where we look at the three-phase fault. And a three-phase fault is basically a short circuit, and it's a really bad scenario. It's generally a very big fault, and ironically, it's also generally quite balanced. because the connection across all three phases, we assume in this case it's going to be a bolted fault, equivalent of someone throwing a chain over the line. And because that is a load connected along the line, it's still following the convention. Now, the reason why it's going to be so big is that the only thing that is limiting that fault in terms of fault impedance is the chain, for example, and the impedance of the line and the windings of the transformer upstream to the point. It's interesting that despite for all of its size, in theory, you're probably not going to get any negative phase sequence or zero sequence in this fault. It's going to be all positive, and there's going to be a lot of it. So for this application, earth fault and NPS probably won't see it. But if we have a look at some of the other fault conditions, like a line-to-line, the line-to-line fault is also big because the only impedance is the conductor and the winding of the transformers up and to the point. But in this case, the negative sequence and the positive sequence current are equal in this, in theory, right? And because there is no earth path for this scenario, you're probably not going to get any zero sequence current in it. So it's interesting that under this fault scenario, you would get a pickup, provided that the pickup level was set low enough for both overcurrent and for negative phase sequence. In the case where your fault current for line to line is going to be close to the load current, negative phase sequence will still pick this up because you would assume under a healthy network that you have a relatively low level of negative phase sequence protection, negative phase sequence current. So it gives you a little bit of an ability to be able to identify line-to-line faults when your overcurrent is starting to reach what your load is, because it is the NPS is only looking for the imbalance. It's not looking for the total magnitude of each individual phase. Single line to ground faults as well is a very unbalanced scenario, and also it's probably 80% of fault cases for overhead lines. It's generally the smallest magnitude fault, and the zero sequence impedance varies based on your earthing, but because we're connecting them all in series, they're probably going to be fairly close to each other for this particular fault. So it's an interesting scenario where if you have this kind of fault, you are going to see some amount of each of those individual components turning up. Then if you look at a double line to ground fault or a single line to ground when you have earthing at both sides, you have a very unbalanced fault. And these guys can be pretty big because the impedances are connected in parallel. So when that happens, you tend to reduce the amount of impedance to the fault side. Not quite to the full degree that you would get on a three-phase fault, but it starts to approach there. And sometimes when these faults go uninterrupted, they will cause a three-phase fault. So it's something that you'll certainly want to be able to detect. But broadly speaking, double line to ground faults and your three-phase faults are going to be ones that you're probably going to detect with conventional overcurrent and earth fault. Line to line also to some degree, provided that there is enough differentiation between your load amount and what the fault current looks like. But when you have a look at a broken conductor fault, it's a different case. And the reason for that is that a broken conductor can include the load impedance as well. So it does vary quite a lot depending on your network earthing philosophy, right? So it does change. On a three-wire network, where I've got on the left-hand side there an example where it is ungrounded, if you have a broken conductor on one of those phases, it winds up being that your I2 is actually equal to your I1, which is quite interesting. And then if you look at a four-wire network, because you have an additional path of current, you actually connect all of those sequence components in parallel, the impedances. So it starts to look a lot like a double line to ground fault. The only difference is that you've got your load impedance included as well, which means that your fault current is not very big at all if you're looking at it in terms of an individual imbalance. So the reason why you need negative phase sequence protection is that it provides you the ability to detect not only overcurrent scenarios, but undercurrent scenarios too. So in the event that you have a broken conductor, it gives you a way to be able to see it. And likewise, if you have issues where you are starting to see that the load current, or you might, for instance, have a short-term overload that you can take on. So some circuit breakers have an overload that you could, in high demand, provide extra power for a short period of time. But if that's starting to encroach on what your protection configuration is, negative phase sequence gives you a way to pick out those asymmetric fault conditions because it's looking for imbalance. In a healthy network, you're probably not going to have an awful lot of negative phase sequence there. So when it shows up, it generally means that you have a fault, and it's something that you can use to be able to detect these fault cases that are not necessarily being caught by overcurrent and earth faults by themselves. All right. And that basically gives you what the direct applications of negative phase sequence protection are. Now, this is in the context of line protection. You can also use negative phase sequence protection for motors and for generators, because obviously the loss of phase on any of those particular assets can cause some significant damage very quickly. And traditionally, when that is applied, that's using a very different principle. Well, it's using the same principle of operation, but the settings parameters that you use for that is going to be considerably different. So you need to think about the context under which you apply this protection to make sure that it's appropriate for the scenario that you are using it. In our case, we're talking about overhead lines or underground cable and the distribution network. So we're very much talking about detecting cable discontinuities and detecting line-to-line faults on these long, lightly loaded feeders. So general concepts and the general rule with negative phase sequence is that if you set it to a third of your overcurrent pickup, it's going to have equal sensitivity to line faults. Now, you got to be careful because some relays, instead of operating on I2, they operate on 3I2, so they don't apply that third to it. So before you apply this to any protection in the field, make sure that you're careful with that. In our equipment with the OSM recloser system or the GMK underground cable protection devices, we take the sequence component for NPS, but overcurrent itself works on just the phase values that you see. Now, the general principle here is that the lower that you can set I2 without spurious tripping, the more sensitive you are to imbalance. And provided that you stay above 30%, you're unlikely to run into coordination issues with overcurrent for line-to-line faults. Hopefully that is a generally clear thing for what you can use negative phase sequence by itself to be able to work this out. Now, likewise, negative phase sequence protection could actually be used to detect broken conductors. That's not specifically broken conductor protection as defined by the ANSI 46 BC protection capability, but it really is just applying negative phase sequence to detect the broken conductors. The example on the right-hand side there is if you've got an ungrounded network and you have a discontinuity on one of those phases, then inherently, even though the current includes the load, your I2 is equal to your I1. So if you have I2 in this scenario, you can tell that there is a broken conductor, even though it looks similar to what a load current would be from an I1 perspective. But if you relied only on overcurrent and earth fault, you would miss this and you wouldn't be able to pick it up. And through practical experience, we've heard of many cases where if you don't apply some form of detection for this, for example, on a rural line and you have a cable break, the cable may be hanging off the line and it might come into contact with wildlife over time. And unfortunately, as more and more wildlife turn up to investigate what has happened beforehand, eventually the fault with not too much imagination becomes a phase to ground fault as there is sufficient body between the cable and the ground, and then earth fault takes over. Now, ideally, you don't want to have that scenario. You want to have it that you can at least understand what's going on with the content just before that fault occurs. Well, not before the fault occurs, but whilst it's still simply a floating broken conductor and not a cable on the dirt. So the catch is with doing this is that you somewhat need to know what the negative sequence and positive sequence load and line impedances are. Now, you can work that out, and a lot of protection software helps you out with doing that. So you can do it. And hopefully through discussing this at sort of an empirical level, it gives you a better conceptual understanding about how this functionality fits together. So the goal then is to set your negative phase sequence protection low enough to select that case, but also to reject your general imbalance. Now, if you're in the US and you're using a 4-line system, you do have cases where you are going to run under general imbalance. So that is going to require a very different application case to the 3Y networks, even when the earthing is aligned with showing a 4-wire system. And I'm going to show you what that looks like when we get to the broken conductor protection. I see a question came through with regards to slides being emailed to participants. We're going to be sharing the video with you guys of this entire presentation too, so you'll be able to have a look at that as well. All right. So that's negative phase sequence protection in general. What we want to take a look at now is the ANSI 46 broken conductor protection. And this really is an extension of negative phase sequence protection in and unto itself. Because if you take a look at these two scenarios, so we've got a system normal on the right-hand side there, and a 3-wire network ungrounded with a broken phase. What is the relationship between your I2 and your I1 in this scenario? The interesting part about it is that because they're quite close together and in the same system, your I2 and I1, if you were to look at the absolute magnitude of these, they're going to be pretty close to being equal. So it doesn't actually matter so much what the impedance is along the line if you're only looking at a ratio of I2 on I1. And inherently, that's what broken conductor protection is. It's taking the ratio measurement of the negative phase sequence to the positive phase sequence and using that as the protection operation rather than the absolute magnitude of each of those individual negative phase sequence components. Okay, so by looking at the comparison between I2 and I1, you can then infer what sort of fault is ongoing on your network to be able to get some real clarity about how that system is behaving. And you'll see in the system normal, there really shouldn't be any negative phase sequence in theory. Okay, there might be some in practice, but you can see that we've got a really clear differentiation between the broken conductor scenario and the system normal scenario. So theoretically, you can operate on that quantity. So for a 3-wire network, and in this case, I'm going to assume there's no earth leakage. If you have a broken conductor, you're going to have I2 that's equal to I1. So if you wanted to operate on that metric, an I2 and I1 ratio of 100% will tell you that this is the scenario that's ongoing. So system normal, you expect around 0% because there shouldn't be very much negative phase sequence. And then when you have a broken conductor on this network type, it's going to be close to 100%, even in real world applications. So it becomes really clear, this difference between those two scenarios. Now, that's a really high level look at it, and there are a couple of complications that we have to take into account here, particularly around when you apply it to a 4-wire network, or if there's earth leakage, or if there's additional path through earth, and lastly, if there's any load current that is a little bit too low to be able to give us a stable I1 denominator. So let's firstly take into account the earth leakage scenario. So let's assume that there is an earth fault here. It can be, it might be a small one, but in this case, you can see that I1, I2, and I0 are all connected in series. If you've got an ungrounded transformer, we're thinking back to the 3-wire network. So again, I2 and I1 in this scenario is 100%. But likewise, if you actually have just an earth fault and not a broken conductor, it would also trigger broken conductor because you would then have a ratio that doesn't necessarily dictate that this is the scenario. So in this scenario, you can solve this with a time delay because if you grade your broken conductor with your earth fault protection, you'll be able to differentiate that, okay, this is a floating conductor or this is a cable in the dirt and be able to protect on that. If you look at a broken conductor when you have grounded transformers, a grounded network, or you have a 4-wire system, you actually have an additional path for the current to take. And really, the 3-wire system becomes a 4-wire system going through that earth leakage path. Now, what that means is we have to incorporate and account for zero sequence, negative sequence, positive sequence impedance, all connected in parallel. And therefore, it's not quite so clear cut. You're going to wind up with a value that is probably between 25% up to 50%. But you might need to do a little bit more calculation to catch this scenario as well. Now, I'm going to give you an example of this where we've done the calculations to show you. And we also have an application note that will go through this in full granular detail. So if you want to go through that, then you can just let me know. Drop me an email and we'll get that sorted out. And the last complication that we need to discuss really is, what if the load current is really low? So at low positive sequence current levels, or low load, it doesn't actually take an awful lot of negative phase sequence to shift the ratio. And this is a problem on rural lines, particularly on 4-wire networks, where occasionally if you trip an individual phase, you're going to be well over the 20% threshold and you haven't actually got a broken conductor scenario. Same deal is with if you have imbalance on your rural feeders. Say you've got 10 amps of positive sequence, it would only take 2 amps at NPS to cause a protection operation. And if you've got it configured to trip on that basis, that would be all that it is. So the higher your load current, the less of an issue this becomes for the 46 BC calculation. But to solve it, if you set a minimum load current for the operation, it basically gives you a limit to help mitigate those various trips at the very low load current. It is a shortcoming of 46 broken conductor, and it means that it can be a little bit less reliable on low load networks. Now, we have developed other protection functionality that can help to address some of the high impedance faults on low load networks too, but maybe that can be a subject of a future webinar from us. All right. I've got quite a few questions there as well, but I'll save the rest of them for the end of it. I just want to get really quickly through a practical example. I know we've got a few people joining us from the States and it's getting pretty close to midnight, if not later. So I'd like to get through those quickly. This is the overview of all the protection functionality that is available in these reclosers that you've seen throughout all of the slides. So today, what we've been working on is the overcurrent relay, the 50Q, 51Q, and working with the 46 BC broken conductor protection, right? And it is only a small subset of the information there. So what I want to be able to do just really quickly is show you how you would configure this in a Noja Power recloser and also how you can test it to give you a way to be able to demonstrate what it looks like. And maybe even a way for you to test this in your own network to just sort of dip your toe in this functionality rather than taking a full commitment to it. In terms of configuring it, in a Noja Power OSM recloser, provided you have 116 firmware and above, you would just need to go to I2 on I1 protection, which is part of the common group settings, and then you could configure your pickup value. By default for us, we set it at 20% because at least in 3-wire networks, that's a fairly safe amount. Provided your minimum I2 is 15 amps, that is going to catch most of the cases and give you sufficient selectivity without spurious tripping. You'll also see that we've got a longer tripping time because that also prevents the spurious tripping due to earth faults on that network. Now, if you're only embracing this for the very first time, one of the things that you can do is just configure it to set out an alarm. So this doesn't necessarily cause the breaker to operate. You can make it choose to do so after time, but that alarm you can then feed back via SCADA to say, okay, there's probably a broken conductor on this line and it's something that you need to be aware of. That might even be useful if you have a different class of fault that's going on there, because you can alert your operations team to look for that class of fault, that it might be a blown bridge or a conductor down or so on. So it gives you in a way to be able to address that. So let's have a practical example, all right? This is an example where you've got an earth transformer on both sides and we've blown a fuse or there's a floating conductor on phase A. So there isn't a ground fault included. I'm going to put a couple of extra values in there as well. I'm not going to go through it in great detail because it'll take too much time here to do it, but I do have an application note for you if you need to get that. So please just let us know after the event. You can speak to your Noja Power representative and they can then provide that to you. But in this scenario, we basically derive that our currents are going to look like this because we have a broken current on phase A, so obviously that's 0 amps. And then based on our calculations and the connection of the sequence components together, we derive the 410 amps on phase B, 506 amps on phase C, assuming that this was a 400 amp nominal connection. This is a 34.5 kV system. So if we were to simulate this with the CMS software, we would just load in these. We've got 2 different stages here. You can see the standard 400 amps. I'm assuming a power flow direction ABC to RST. And I've got an initial condition there of a healthy state, and then we have the phase discontinuity for whatever reason. And of course, if we run that through with our software simulator on the controller, we can then see that in this case, we've configured it to trip to lockout. And for this scenario, we've got 46%. Now, if we think back to how we were trying to conceptualize how these different sequence networks connect together, 46% sounds about right. Because if we go back to this, in our fault current calculations, we see that there's an earth path on both sides. So you are feeding it from both sides. Now, because of that, you're connected in parallel. So it's not going to be a case that I2 is equal to I1, and therefore it shouldn't be 100%. In this case, it's going to be a bit lower because they're connected in parallel and not in series. So empirically, 46% seems about right. So that is something that you would have as an expectation for that scenario. And again, had you set this at 20 amps, at 20% I2 and I1, you would have caught this. But if it's a 400 amp network and suddenly you've gone up to 506 amps, that's not necessarily going to get caught with your overcurrent. So it is a case where you can see that, and that you would then be able to pick up that fault condition as being a phase discontinuity. In the event, so let's go to one where it's slightly different. And in this case, you have an ungrounded transformer on the far side, right? So we still do have a ground reference here because you've got a delta star with a grounded star at the source side, but then a phase A open, a phase A disconnect and an ungrounded side on the load side as well. So let's assume same nominal current, power flow direction, ABC to RST. This time around, when we think about it, we're actually going to connect all of them in series. They're not going to be connected in parallel because that is the network topology for this class of fault, right? There isn't an additional earth path for the current to flow. So in this case, 400 amps, IB and IC are 405, 405. And actually, if you look down below at this calculation, your neutral current is still theoretically zero. So that already shows you that the zero sequence is going to be uninvolved in this particular calculation. So when we go to work it out, we sub those in, we actually run the simulation. Of course, turns out I2 and I1 comes back as 100%, which again aligns with the topology that we defined before, where we said that if it's ungrounded and you have the floating broken conductor, I2 and I1 are equal. Therefore, I2 on I1 is 100%. So again, you're able to detect the scenario, and very clearly in this case, if you didn't have negative phase sequence or broken conductor protection, you're not going to pick this up on overcurrent, and you're definitely not going to see it on neutral overcurrent either, your earth fault protection. So it does help you address a blind spot in your protection calculations or in your protection schemes to identify these broken conductor faults. All right. So in summary, we covered phases, we covered symmetrical components and how to get them from the phases, and we covered the most common faults on the network. So going for single phase to ground faults, and we talked about double line to ground faults and three phase faults, and also the broken conductor fault. Now, broken conductor ones, they included the load in them as well. So we started to see the problem of relying only on overcurrent and earth fault protection by itself, because it still leaves a blind spot in the calculations. So we then looked at negative phase sequence protection by itself and why we would need it and how to set it and some of the limitations with it. And then also went on to talk about broken conductor protection and how that works and how to set it and some limitations. Now, today, if there is someone that, if you are using our OSM recloses, the firmware version, firmware is free today to upgrade to beyond 1.16 to be able to gain access to this. And I think that there can be some really good safety benefits by being able to detect these scenarios, because I've heard of too many cases of having broken conductors with them floating in the air that are going undetected until there is some serious damage done. So it is important to have a technique to be able to address this. All right. And with that, I'd like to open the floor to some questions as well. So if you have any questions, please make sure that you send them through to our system. Let's see.